All right, guys, let's go ahead and talk about today's warm-up question. It's not math or anything, so it's just a quick little typed explanation. So hopefully you are able to come up with an explanation for how to walk. Okay, and it says be specific with words like push or pull. So how do you walk if you're explaining it to someone? What did you guys say? Emily, what did y'all say?
I have no idea what I mean.
All right, let's tell me how to walk. What do we do?
I don't even know how to explain it. Like what? Yeah, lift up your foot.
Lift up my foot. Okay. Okay.
And then.
What do you got, Vivi?
You lift up your foot and then
I got that part.
it in front of the other foot and then repeat.
Push your foot off the ground.
Push my foot off the ground. Okay, lift my foot in front of the foot. Repeat, push foot off the ground. What do y'all got?
When your foot's in front, you're pulling, and then when you go to the back, you're pushing.
Pushing and pulling on what?
The
Your
ground.
muscles, the ground.
The ground, the muscles.
Pushing off the ground.
Pushing off the ground. Okay, which way do I push off the ground?
Forward.
You push back.
Oh, wait. Backward.
Push backwards off the ground. Okay, to move forward. Okay, so again, put some words in there like push and pull and like you guys just said, pushing off of the ground. So that you have an explanation there for how to walk. Okay, and if all you're telling me is push down on the ground, then that's this. Some of you will probably read that, but I'm not going anywhere. Okay, so make sure that you're also using directional words as well. But yeah, if you're pushing backwards on the ground, you will move forward. And we're going to talk about that today with our notes on third law interactions. You do have a My Open Math assignment today, 401.4 third law problem set, but it's due tomorrow. Okay, so I know some of you finished yesterday's assignment, some of you didn't. So those of you who didn't finish yesterday's stuff, you'll have a little bit of, potentially have a little bit of time to work on that, but you're now a little bit behind because you also have this assignment due tomorrow. But just keep that in mind, make sure you're managing your time there. All right, so let's go ahead and get into today's notes. This is familiar because we've seen this slide before. But when we're talking about these interactions, we need to go back all the way to the definition of a force, which is actually how we started our last unit. Okay, so a force is a push or a pull on an object resulting from an interaction with another object. Forces are vector quantities and they are measured in newtons. And we've seen this exact slide before and this exact example of this baseball making contact with a bat. Okay, so whenever we talk about a force, it's always going to involve at least two objects. Okay, whether it's this example with a baseball and a bat, or whether you're talking about slapping somebody across the face, you have hand face. Okay, but you're going to have two objects. It's an interaction between objects. In this example, we could say that the bat pushes the baseball forward whenever they make contact, and you will use words like push or pull in order to describe the forces, the interaction between those two objects. Okay, so because forces are interactions between two objects, Isaac Newton referred to these forces as action-reaction force pairs. Okay, so we're getting into third law because Newton's third law describes the nature of these forces in an interaction between two objects, stating, this is the third law down here at the bottom, for every action there is an equal and opposite reaction. And I know you've heard that before. Okay, this is Newton's third law. We've already talked about his first law. That was the law of inertia. Okay, that's an object at rest will remain at rest. An object in motion will remain in motion with constant velocity unless acted on by an external force. Okay, and then we talked about Newton's second law where we said that the acceleration that an object experiences is directly proportional to the force applied to it and inversely proportional to its mass, and we summarized that with the equation F net equals ma. That's his second law. This is the third law. Okay, for every action there is an equal and opposite reaction. Okay, so he's only got the three, so you know all of the laws now. But this is going to describe the interaction between these two objects. So we're going to talk about action force and the accompanying reaction force because, again, it's a pair. So whenever you have the bat hitting the ball, you also have the ball hitting the bat, okay, in that previous example. But we're going to look at some different force pairs today. Okay, this means that a force exerted on one object will cause a force of equal magnitude but opposite direction on the other object in the interaction. Okay, so again, because for every action there's an equal and opposite reaction, if, again, like that first example in the definition slide, whenever the bat hits the ball also hits the bat. And those forces that they experience are equal and opposite to each other. That's what Newton's third law says. So let's go ahead and see if we can identify a really basic, easy force pair. Okay, so interaction force pairs, step one is going to be to identify two objects involved in the interaction. So I'm going to give you an easy example, and I think we looked at this last unit as well. A book is at rest on a table. Okay, and so looking at this, we're going to identify the two objects. We're going to go with book and table. Could you pick other objects? Sure, if you wanted to, but we're going to go with the most basic objects here. Okay, I'm not going to include the floor or anything else right now. Okay, so book and table. Okay, your step two of identifying your force pair is to describe the push on one of the objects, and it could be push or pull, and include a directional adjective. Okay, something like this. The book pushes down on the table. So I used the word push. Again, it could be push or pull. I have a directional adjective. It pushes down. Okay, down is that in the direction, and I have my two objects. So book pushes down on the table. Okay, so that is describing one half of my force pair, because we said for every action there's an equal and opposite reaction. So I could think of this as my action force. It's pretty boring in terms of action, I guess, because it's not really doing much, but it is. The book is pushing down on the table. Okay, the third step is to describe the push on the other object and include a directional adjective. The two nouns in the sentence switch locations. So I had book pushes down on table. Now I have table pushes up on book. Okay, the direction is opposite. The first one was down, this one is up. And the order of my two nouns in my sentence, table and book, are flipped. So it's basically we had book pushes down on table, now we have table pushes up on book. Okay, really basic. I'm pretty sure y'all could do this, but that's the steps for going through it. And so this is your interaction force pair. The book pushes down on the table. The other half of that force pair is the table pushes up on the book. Okay, so you can do this with an interaction between any two objects. It doesn't have to be a book and a table. It can be anything. So long as you have an interaction between those two objects, you have a push or a pull, you have a force there, then you can describe this force pair. And again, these forces would be equal and opposite to each other. The force with which the book pushes down on the table is equal to the force with which the table pushes up on the book. Okay, so again, this is the one we just did. Force of table on book equals force of book on table. You can also write it like this. You'll notice I made them equal and opposite to each other. Okay, because the table is pushing up, I went ahead and called that positive. Because the book is pushing down, I went ahead and called that negative. To make it so you don't have to write something that long, sometimes you'll see it written like this. Force of table on book equals negative force of book on table. So this is also an acceptable way to write out your force pair. Okay, now we've already labeled these actual types of forces as well. Okay, like normal force, and so you can also use those terms that you're already familiar with. But you need to be able to identify where the force pair exists between two objects, or the other half of the force pair. If I say, hey, here's a force, what's the other half of this interaction? Okay, so let's draw a free body diagram for the forces acting on the book at rest on the table. Okay, and so my free body diagram, I'll start with my book. Okay, and in my free body diagram, I'm going to draw that force of the table on the book. There's my normal force, okay, because I have that written on my screen right now. Okay, so I have my force of table on book right here. It's Fn. What other forces are acting on the book? If we draw a free body diagram, what else do we need to draw? Gravity. Okay, so I'm going to also draw in Fg. Where is this one? Does where is the force of the book on the table go in my free body diagram? The answer is it doesn't. Okay, that force is not acting on the book. It's what the book is doing to something else. Okay, so your free body diagram will not include both halves of your force pair. FG and FN, are they a force pair? They are not. Okay, FG and FN are not a force pair, and this is a very common misconception because FG and FN in this example and in most examples are equal and opposite to each other. But they are not a force pair because they're not an interaction between the same two objects. The force pair is the table pushes down on the book pushes up on the table. That's the force pair. Okay, whenever I talk about FG is a force between the book and the earth. The earth's gravitational field pulls down on the book. That's where its weight comes from. Okay, and there's another half to that force pair too. The book pulls up on the earth, which sounds weird, but that is the other half of the force pair because any two objects with mass will exert a gravitational force on one another. Okay, which means, and I'll get to it in a minute, actually, I'm getting ahead of myself. Okay, so this is another tool that we can use to help illustrate force pairs. It is called a schema. Okay, so a schema will show all the force pairs between multiple objects in a scenario. The free body diagrams that we've been using only show the forces on one object, but there are multiple objects here. There's the book, the table, the earth. We could include other things. If you wanted to make it way more complicated, you can include a lot of other things that are in this scenario, like the floor. Okay, but I'm going to stick with and try to keep it a little bit more basic. So I'm going to stick with just book, table, and earth. Okay, and so you can see the force pairs represented by these arrows. So this blue arrow here is that force pair we initially talked about that exists between the book and the table. We said the force of the table on the book equals the force of the book on the table. We said that the table pushes up on the book pushes down on the table. That's that force pair. We can also label other force pairs in this interaction. Okay, obviously we know that the earth is there, and so we know that the earth will exert a force. Well, technically the earth's gravitational field will exert forces on any object that is, on its surface or in its vicinity. Okay, and so we could also say that the force of the table on the earth equals the force of the earth on the table. The earth pulls down on the table pulls up on the earth. Okay, same thing here between the book and the earth. We can say that the book pulls up on the earth pulls down on the book. And these earth pulling on book and earth pulling on table, this is where the weight comes from. Okay, they are downward forces, they are negative, and that is where the weight of the book comes from, that is where the weight of the table comes from. Okay, so you have different force pairs, but when you draw a free body diagram, these aren't all in your diagram. Okay, the free body diagram shows the forces acting on a single object. And so you're not going to see every single force that's in your schema in your free body diagram. Okay, now I will tell you this, typically we use schemas as a tool to help us see things like force pairs and to help us figure out how to draw a free body diagram, but we already know how to draw a free body diagram. Okay, this is a helpful tool to help you learn it the first time if we start with Newton's third law, which we didn't because of the way we had to break our unit up this year. Okay, but again, here's that same schema. You can see the different forces here, but the only two that would show up in a free body diagram, and I forgot to change this. This is supposed to say book and table over here. I did a different one. But it should say a book sits at rest on a table like it did before. But these are your force pairs, okay? Book pushes down on table pushes up on book. We've already talked about that one. That's, again, the table pushing up on the book is the normal force that we see here. And these other ones, earth pulling down on table pulling up on earth, those don't show up in my diagram because I'm looking at just the book. So when you draw a free body diagram, you look at just one object. And if I look at just the book over here, there are only two forces acting on it. This half of this blue one, which again is the force between the book and the table, and it's specifically the table pushes up on the book, and this half of the green one, okay, which is the force of gravity between the earth and the book. Okay, and that's, of course, FG and FN over here. So again, when you draw your free body diagram, you're only drawing the forces that are acting on that one object, whatever object you're drawing it for. In this case, I did it for the book. All right, so again, Newton's third law, for every action there is an equal and opposite reaction. Right now, the earth is pulling down on you, not just that book, but also on you, giving you your weight. Let's call this the action force. Again, action-reaction force pair. So the earth pulls down on you. What is the reaction force to the earth, or the force of the earth pulling down on you? What did we say that it was? That is the type of force. It is a force of gravity. But the earth pulls down on you. You pull up on the earth. You also have a gravitational field. Now, compared to the earth, it's pretty insignificant. But you are, in terms of the acceleration of the earth, you're not going to see that there. But technically, the force is the same force between you. Again, equal and opposite. The amount of force that you exert on the earth is equal to the amount of force the earth exerts on you. The difference is the earth is massive compared to you. So you're not going to see the effect of it. Okay, but the forces are equal and opposite. Okay, so the reaction force is you pull up on the earth. This is a silly clip from Family Guy. Let's see if I can share my audio because I just realized I didn't turn that on. Hold on one second. So again, any object with mass will exert a gravitational force on any other object with mass. And again, this is a silly clip. But
All right, watch this.
What the heck?
What the heck?
What is this?
What is this? What is this, some kind of gag? No.
Orbit.
It's orbit. Huh? You have your own gravitational pull. Oh, that's a bunch of crap.
Now back to the Three Stooges.
it's obviously a silly example, but in this episode, I think they're talking about how he gained more mass, and so now he has an even greater gravitational field around him. But you do have a gravitational field as well. Any two objects with mass will attract one another with a gravitational force. So the earth does pull down on you, but you do pull back up on the earth with an equal and opposite force, which sounds crazy. And it sounds crazy to us because we don't think of ourselves pulling up on the earth. And in terms of the effect on the earth, you don't have one really, because your mass is negligible in comparison to the mass of the earth. And so that force doesn't create change in the earth. And that change would be, of course, acceleration. You accelerate, you fall, okay? But the earth, that acceleration there is going to be much smaller, even though the forces are equal. And we're going to get to another example to maybe illustrate that a little bit better. Okay, so it says, which force is greater? The force of the cannon on the cannonball or the force of the cannonball on the cannon?
Equal.
They're equal. Guys, this is the type of question you're going to see on the test. And this is also, again, a very common misconception because students see this and they say, well, the cannonball's moving a lot faster. It probably had a greater force on it. And I can understand your logic, how you got there, but it's wrong. The forces are equal and opposite. That is what Newton's third law states. For every action, there's an equal and opposite reaction. Equal and opposite. Okay, so the force of the cannon on the cannonball is equal and opposite to the force of the cannonball on the cannon. When a cannon fires, that cannonball, yes, is shot forward really fast. The cannon rolls back pretty slow. Okay, and the reason for that vastly different acceleration is because they have vastly different masses, in the same way that you and the earth have vastly different masses. It all goes back to Newton's second law. F net equals ma. Those forces can be equal, and they are, not can be, they are. Okay, but they're equal to mass times acceleration as well. That means the mass times acceleration of the cannonball equals the mass times acceleration of the cannon. And when their masses are different, their accelerations will be as well. Okay, same thing with you and the earth. Your mass is tiny compared to the earth's mass. Okay, so whenever we look at that force pair, you have the mass of the earth would be very large. Okay, a very small acceleration, and your mass is very small, and you therefore have a very large acceleration. Okay, they're equal to each other though. The forces are equal. Okay, but if your mass is 10 times bigger, then your acceleration is going to be 10 times smaller, okay, compared to the other object. So again, it goes back to Newton's second law. The forces are equal. They're going to cause unequal accelerations, though, if their masses are different. If they have the same mass, then they're going to have the same acceleration both ways. Okay, but if you have an object that's vastly bigger than another object, even though the forces are equal, the accelerations, of course, are going to be vastly different because those forces are equal to mass times acceleration. Okay, so which has a greater acceleration, the cannon or the cannonball? It's not a trick question. The cannonball. Okay, again, it's this right here. Okay, the cannon has a big mass, a small acceleration. The cannonball has a small mass, relatively, and therefore a very large acceleration. Okay, but the forces are equal. Okay, it's a force pair. Okay, so again, very common misconception. Force of the cannon equals the force on the cannonball. They're equal and opposite. Same thing though. A large mass of the cannon, you're going to have a smaller acceleration. With a smaller mass of the cannonball, you're going to have a larger acceleration. Okay, but again, you will see this on the test. I don't know if it's with a cannon and a cannonball, but you will see this on the test, and it is a very common misconception because people always want to tell me the cannonball has more force acting on it. It doesn't. It does have more acceleration, though, because it has a smaller mass. All right, so again, Newton's second law, talked about it a lot. But it states that the acceleration of the object is directly proportional to the net force acting on the object and inversely proportional to the mass of the object. So those larger forces cause larger accelerations with equal masses. We're not dealing with that here, though. We're talking about a force pair, so our forces are the same size. But look at that second bullet point. Larger masses accelerate less when forces are equal. Okay, when forces are equal, that's right now. We're talking about equal and opposite forces. Larger masses accelerate less. Okay, when you have equal forces. And the opposite's also true. Smaller masses accelerate more. All right, guys, so that's it for today's notes. We've covered, again, a good chunk of what you're going to see in that assignment, but we do have more notes tomorrow to kind of finish out Newton's third law with some more stuff. So if you open up today's assignment and you're not sure how to do some of the questions, you don't have to answer all of them. It's not due till tomorrow. You can hold off on that one, or you can ask me. But it may be answered in tomorrow's notes is my point. So again, go ahead and get to work on this. And if you have questions as you are working, let me know. And then also, if you didn't finish yesterday's assignment, you now have 25 minutes left in class. Now, yesterday's assignment at this point is going to be late, but please work on it if you don't know how to do it. You've got time. You can ask for help while you're in here. You can also get started on this one. But everybody should have something to do. If you have any questions, please let me know.